Hi everyone, let's get started. Since we are kind of behind schedule, I'm ZX. I'm working on Filecoin Economics, protocol apps, but today I'm talking to you about some of the thesis research that I've done with Michael and the Warren Center of Network and Data Sciences at UPenn. It's called Engineering Token Economy with System Modeling. So in today's talk, I hope to present to you a model and a simulation of a generalized token economy so that we can apply some of this concept that we talked about earlier today in a more concrete sense. All right, let's get started. So to start off, what is a token economy? I think in some of the talks yesterday we talked a lot about what is a token economy. Basically, on the highest level, it's an economy that pays out token for any provider that provides goods and services for the network. In a new Cypher's case, that would be key management system. In LivePeer's case, that would be video encoding. In Filecoin's case, that could be file storage. In Ethereum, there would be computation. In Bitcoin, there could be security. So any of this economy, as long as there's a provider providing some goods and services, and then they can get paid in cryptocurrency or token, we call that a token economy. And the next question to ask is, why do we need to do system modeling for these token economies? I think the short answer is cryptoeconomics is hard because you need to understand all the different moving parts in your protocol, from cryptography to distributed systems. You need to talk to the product team and biz dev team to know what is the goal that the system is trying to achieve. And as mentioned earlier in the talks today by Michael and Sherman and Chris, it's all complex systems at the core. So some of this patchy solution that people are trying to do today in the past could lead to really bad system failures. That's why it's really helpful for us to model the system as a whole and see how the system can evolve and how the goals can be achieved and what are the constraints of the system. And lastly, I think sometimes some of the recommendation from some of the recommendation or decision from an economic standpoint are hard to visualize what exactly is impact on the system. So having a model on the whole system itself will allow us to articulate that impact and justify the decision much more easily. So here's a generalized framework. I think it shows up in some of this diagram shows up in some of the past presentation today. So basically, we draw inspiration from some of the differential game literature in the past that irrespective of the agent specific behavior, we still want the system level goals to be achieved. So basically, as protocol designers, we design policies and mechanism of the protocol. And then for agent in the system, they basically respond given some external noise. It could be the market activity, it could be anything. And then it will look at the system global state and then derive a private belief about their signal. What do they believe? What is the profitability right now? What do they believe about how the system is going to evolve? And then given the allowable policy space that we define as protocol designers, agent will make a decision about given all these states. And from there, given all this action, we'll be able to generate state updates through the mechanism steps, and that will give us the next state of the system. And from here, we want to propose or want to come up with a simple model or simulation such that we can have a very baseline economy token economy, and then we can run experiment on this economy and see how our decision on a protocol standpoint will affect macroeconomic behaviors. So to do that, we need to first make two simplifying assumptions such that we are not really bogged down by these details, and then we can look at the system economy as a whole. The first simplifying assumption that we are making here is we are assuming that every miner or user, they are identical to each other. We call it unit miner or unit user, and each of them consume or produce 1 unit of service. I think in Yongdong's talk yesterday, he talks about how do you define a unit in LivePeer's case. Similarly, I think for the sake of our model, we just treat that unit has been defined, and then there will be different unit miners and unit user providing that service or consuming that service on the network. And a large miner in real life would be an aggregate of many unit miners in the model. The second assumption is we assume that it's because for a simple model, we just assume a perfectly competitive market so that we don't have to worry about a lot of the dynamics within the price. We just assume that price would be a very effective signal about the supply and demand. When there's supply meet demand, there's always a transaction that's happening. And from here, we want to define this system both in terms of its system state and also like the system dynamics. Because what the system states are and how the system can evolve, it basically encapsulates the entire token economy. So even for a very simple, like bare bones simple token economy, we can easily have more than 10 states. So here's how this works. This is a token economy of supply and demand of goods and services. So you have the supply of the goods at every particular time around t, which could be any time step that you define. It could be as granular as like at every block, every day, every week, right? And at every time step t, there is some supply and demand coming to the network. So there will be like the delta S and delta D at time t, and then there will be some departure of like the supply and demand. And then at the end of the time step t, there will be some supply and demand. It's on the network, and given the perfectly competitive market assumption, we assume that some quantity will be transacted at a time step, and then there will be some market price, which will be Q and P. And then there's also a token price, which is K, and K is a function of like it's a combination of the intrinsic value of the token plus some speculative value of the token. Right now, like I think we don't really have a very good definition for most of the token today. We don't have a good definition of what the intrinsic value is. But in some of the past research that's done by Claudio, people define that as what is the fiat amount of resources that you need to spend to earn 1 unit of the token. In some of the past research, like people define that as the intrinsic value of the token. So we can use that for the model here. There will be the inverse of V over Vt, and Ut will be the speculative value. And then we also define like some kind of abstract index of how far the network is progressing along its goals, which is I of t. So this can be useful in terms of our own engineering block reward such that it targets this particular KPI the network is trying to optimize for. In most of the cryptocurrency network that we see today, people use an open loop block reward schedule, like in Bitcoin, right? Like the block reward has nothing, in that context, basically that KPI is basically time step. So basically what that means is the block reward follows a fixed schedule regardless of what happens on the network. So in Bitcoin's case, there will be like the 6-year half-life that we were talking about. And from there, we define like the state dynamics, the system dynamics. So at every time step, the following things would happen. So some unit service supply and demand arrive at the network, and that is basically driven by the private signals of all the different agents in the system. And then some transaction will happen for the services given the unit service supply and demand. And then block rewards are minted, and miner makes a profit from the system. And that is RT. So basically, that's like how profitable is mining in the network, basically providing that service in the network. And then from there, some speculation might happen that will change the token price, and that will also change some of the private signals about profitability or how cheap or how expensive is this service being provided on the network. And these are the more specific equation that we use to drive the dynamics in this baseline simulation or model. And some of these stochastic processes, they are just examples of distribution that we can use to drive those signals. It doesn't have to be this specific distribution. You can always customize that depending on the specific token economy that we're talking about. So the variable supply and demand, we've used a traditional like Poisson distribution process. The mean of that distribution would get greater if mining is very profitable. In terms of supply, more supply will arrive to the network when mining is very profitable, which makes sense. That is in the lambda S equation. And more demand will come to the network if the goods or services provided on this network is really cheap. If the price is going down, more people will come in. We assume that there's a demand for these goods and services on the network. More people will come to consume that goods or services. And from there, we can figure out the supply and demand. And then given that the price can be determined and the quantity as well, and the block reward, let's say we assume the block reward targets this goal the network is trying to optimize for. And in most cases, in open loop setting, that would be just delta t. So it follows like a predetermined timetable of how block reward is going to be injected into the system. And then K of t, which is the price of the token, which is would just be a combination of the intrinsic value of the token and the speculative value. And the speculative value could be, we can put in an agent policy that is, agent we're trying to estimate what is the immediate reduction in supply of the token. If there's an immediate reduction in supply, people will try to speculate, and that will drive up the speculative value of the token. Or people need some kind of hook to basically speculate and drive up the value. And then we define a cost. Cost will go into like how profitable it is for a miner or provider to provide that service to the network. And then now we can, so given the definition of the system in terms of system state and dynamics, now we can basically run a very simple experiment to show the power of this, this simulation. So we do a control experiment of, we're basically just changing one function, which is how the block reward is being distributed into the system. The one case would be a simple step decay function like that in the case of Bitcoin. 6-year half-life, 4-year half-life, simple halving period. And then the other block reward schedule could just be a simple exponential decay with the same half-life. We would think that, oh yeah, like a step decay will introduce arbitrary shock into the system. We would think that that's a bad idea from a system standpoint. And exponential decay will be smoother. There will be a nicer system properties. And then we can run experiment to see, just given this very simple change, what is the emergent property that we can observe from the simulation. And as it turns out, with the step decay, which is on the left, and this is the smooth exponential decay on the right, with the step decay, agent will try to speculate around that discrete halving period, and that inject energy into the system. And some of the energy get retained in terms of the token price. And as we can see, there's at least an order of magnitude difference in the terminal token price of the token. And another interesting thing that we observe is this is basically Q. Q is the quantity transacted on the system every time step t. So this is the growth of Q over time. And on the left is basically the step decay function. On the right is the smooth exponential decay. We ran like 100 experiment Monte Carlo simulation on these two different systems. And we observe a general rightward shift in terms of the aggregated growth in Q. What that means is, given these shocks, like we actually can observe like greater quantity transacted on the network, which is, and these two diagrams are actually like internally coherent, because like when the token price becomes greater, mining becomes more profitable. So more miner will come to the network to provide like the goods and services, which drive down the price of the goods and services, and that results in more consumption. So this goes to show that a very simple change in the protocol will have very big impact on the macro and the global level. And to sum up, I think like over here we present a framework to bridge token economies with stochastic dynamical systems. So now you can basically have a model of your economy, and you can reason about how the different pieces in your protocol will evolve, and what kind of change, and all the changes that you introduce into your system, how would that impact the overall economy. And we also have a baseline simulation based on open loop block reward schedule to illustrate this power. As we observed earlier, we only make one change, which is the block reward function, and everything else holds constant. We observe very different behavior in the economy. And which is the second point, where like the agent level incentive would drastically change the global emergent behavior. And there are many other interesting research direction that we can take from here, right? For instance, we make a lot of simplifying assumptions earlier about speculation. We also assume like everything is the same. You can throw in different subpopulation of agents, have different behaviors, and you can also customize of how the dynamics will actually, like for instance, like we use a very simple Poisson distribution for the arrival of supply and demand. That distribution can also be changed. So like there are many interesting work given this generalized framework. And insofar as reasoning through about all of the token economics and all of what impact do you have, I think this generalized framework provides a very good starting point and basis. Yeah, and I think that's all for my presentation. And any questions? Well, thank you. Yeah. Yes.
I saw the simulation results, but I didn't really see any comparisons with existing token economies.
Yeah, so this is like a generalized version of a token economy. So there's no like a specific comparison. Yeah, and
there's a outstanding roadmap item for mapping this onto live peer and a few other things, but it's part of the idea of coming out with the collaborations, looking for basically teams to work on targets. So
Yeah.
Literally, the roadmap is start to map things down onto specific instances and figure out the backtest.
And we can just customize a lot of these like blocks in the dynamics of the system. Just go for it.
How data-driven were these distributions? Like, were they just like distributions that you randomly like thought up based on your understanding of the system, or were they like from actual?
Yeah, so for this model, I think like we derive the distribution from like first principle reasoning and some of the past research literature on what people usually do for similar situation. But definitely this can be, you can throw in like another model here to model that distribution. Yeah.
In applied settings, you usually draw stochastic process models that are fit from real data that's in an analogous system or several analogous systems. But this was from a master's thesis and from a journal paper where the assumptions match the literature as opposed to being driven by a like a project with a team.
Was this implemented in Kafka and can it handle long-term distributions?
Say that again?
Was it implemented in Kafka, this one, and the other one, in this kind of generalist framework or whatever, you can handle long-tail distributions?
Yes, it was implemented in CatCat, and I believe you can put in different kind of distribution in the system. Yeah.
So I'm a program language person, and what strikes me here is that there's a huge gulf between the way in which we express, smart contracts and other artifacts, and the kinds of analysis that we actually need to do, and the kinds of analysis that we're showing. And so I wonder if you or any other speakers we just heard from have thought about tools that we should be using instead, rather than Solidity or similar, to actually express, solutions to these kinds of problems.
I think it depends on the scale. I think like what the scale, where exactly the scale that we're looking at. I think if it's very agent-based up to a specific agent, that we may be able to use like the languages as defined in a smart contract. But I think over here, we want to reason about how the system evolved, what is the goal, and what is the fundamental force and structure. Like we don't really need to go down to that level. But I believe like maybe Tarun's group have done some work in like porting over like smart contract languages into like agent-based modeling. Yeah.